Hello, my name is Jagdeep, and welcome to my presentation. I'm going to talk about Quandle coloring quivers of Torus knots as a joint work with Dr. Carmen Comprau. I'm excited to see what others have to share and want to thank our host for allowing me to participate. So let's get started with some background information and work towards a few results. For our first definition, if we let X be a set and triangle an operation that satisfies these three axioms, we can define the set and its operation as a quandle. The first axiom resembles an identity, the second invertibility, and the third right distributivity. As an example, a dihedral quandle is defined on the set of integers modulo n and an operation given by x triangle y equal to 2y minus x mod n. In this case, we can denote this quandle as its pair of set and operation, or simply refer to them as a Z-Quandle. Another example is that every oriented knot K has a fundamental quandle, which is independent of the knot diagram. In this case, we use the knot crossings in any given knot diagram to form our relations, which can further be reduced. For this relation, if we consider an overstrand Y that is directed in the upwards direction, and an understrand on the right side labeled as X, we label the left understrand as X triangle Y. For an example, we have a trefoil knot that's labeled and oriented. In the case of this crossing at the very bottom, we have that X is the overstrand oriented in the upwards direction and Y is an understrand on the right. In this case, the left side would be labeled as Y triangle X. Since this is the same as the strand Z, we have our first relation. Since there are two other crossings, there are two more relations to consider. Now for torus links in particular, a P2 torus link has a fundamental quandle that can be expressed recursively. And this is done on P generators with relations that use 2 at a time. It's easier to see this with a braid representation of a torus link. If we label it in such a way, we notice that the top, X1, is an overstrand that is oriented in the downwards direction. So in this case, X2 would be the understrand on the right, making XP the understrand on the left. So this means that XP is equal to X2 triangle X1. Now, XP becomes the overstrand with X1 on the right. So this means X1 triangle XP is equal to XP minus 1. And this pattern holds for other torus links as well. In the case of a P3 torus link, our relations would use 3 generators at a time. And for P4, we would use 4 generators at a time. Now that we have 2 examples of quandles, we might consider how they interact with each other. So given 2 quandles, X triangle and Y triangle prime, a mapping psi from X to Y is called a quandle homomorphism if psi of A triangle B is equal to psi of A triangle prime psi of B. A special quandle homomorphism is a coloring. For any oriented knot or link K and quandle X, an X quandle coloring of K is a quandle homomorphism that simply uses the fundamental quandle of K as its domain. With the idea of colorings in mind, we might consider a coloring space, which is simply the collection of all X quandle colorings of K. For notation purposes, if we have a function g going from x to y, where x is a set of little x's and y is a set of little y's, if g maps xi to yji, we simply write this in the subscript of g. In this example here, x1 is mapped to yj1, x2 is mapped to yj2, and so on. This helps us reduce the amount of relations that we have to keep track of when considering quandles and quandle colorings and quandle coloring quivers. Additionally, if we have a quandle coloring consisting only of a single color, we use the term trivial coloring. Otherwise, we use non-trivial colorings. So let's see an example of Z3 quandle colorings of the torus knot T32. This is simply the trefoil knot. And in this case, we have 3 trivial colorings, which are indicated by a single value across the subscript, and we have 6 non-trivial colorings. We might want to consider at this point how the colorings also interact with each other. And that leads us to the next section on Quandle coloring quivers. If we consider a knot or link K and a Quandle X, we define the associated X-Quandle coloring quiver as the directed graph with a vertex VF for every element in our coloring space and an edge directed from the vertex VF to the vertex VG whenever G is the image of F under some Quandle homomorphism from our Quandle X to itself. To visualize this, we use a hot link that has a coloring space of 3 trivial colorings. For each coloring, we assign a vertex, and after considering all the Quandle homomorphisms from our particular Quandle to itself, we find that each vertex is mapped to another vertex, including itself 3 times. Since these graphs resemble complete graphs, we use a similar notation. We have K3 to represent a complete graph on 3 vertices, and a 3 hat to represent a constant weight function, since we have a constant weight of 3. So let's return to our example with the trefoil knot. We had 3 trivial colorings and 6 non-trivial colorings. If we focus on this distinction separately, we find 2 subgraph components that also resemble complete graphs. For the trivial colorings, we have a subgraph that resembles a complete graph on 3 vertices. Meanwhile, for the non-trivial colorings, we have a subgraph that represents a complete graph on 6 vertices. So we use our notation to indicate a complete graph on 3 vertices with a constant weight of 3, and a complete graph on 6 vertices with a constant weight of 1. We also have maps from the subgraph associated with non-trivial colorings that lead to the subgraph associated with trivial colorings. And so the full Quandle coloring quiver looks something like this. If we notice, the vertices in the subgraph associated with our non-trivial colorings map to every vertex in the subgraph associated with trivial colorings, but not the other way around. And so for the full Quandle coloring quiver of the trefoil knot under Z3, we have a complete graph on 3 vertices with a constant weight of 3, joined by a constant weight of 1, another complete graph on 6 vertices with a constant weight of 1. Now in this case, the number of maps we had to consider was manageable, but the number quickly grows with each example. So this leads to our first lemma. If we consider a dihedral quandle, Zn, it turns out there are n-squared quandle homomorphisms from it to itself that have the form phi sub alpha. In addition to this, the alphas can be found recursively. And this is easier to visualize using the operation tables of our dihedral quandles. In the case of Z7, we see that 0 triangle 1 is equal to 2. Since phi is a quandle homomorphism that maps 0 to alpha 1, 1 to alpha 2, we get that 2 must also be mapped to alpha 3. And this pattern continues with 1 triangle 2 equal to 3, 2 triangle 3 equal to 4, and so on. Now that we've seen an example of quandle colorings, and we have a lemma on the quandle homomorphisms also used to form a quiver, we move on to our main results. Let TP2 be a torus link and consider a dihedral quandle Zn. Our first lemma considers any 2 fixed and consecutive arcs of our torus link with labels x1 and x2. If psi is a quandle coloring of our torus link under Zn, then p psi of x1 must be congruent to p psi of x2 mod n. And the idea behind this lemma comes from the pattern that we saw in our fundamental quandles of torus links. We know that xp is equal to x2 triangle x1. This means that psi of xp is equal to psi of x2 triangle x1. As a quandle homomorphism, this is also equal to psi of x2 triangle psi of x1. If we further evaluate this using the operation of dihedral quandles, we find that psi of xp is equal to 2 psi of x1 minus psi of x2 mod n. And if we repeat this for each of the generators in our fundamental quandle, we get a system of equations that we can use substitution on to get our result. This leads to our first theorem on quandle colorings. It turns out that if the GCD of P and N is equal to 1, The Quandle coloring space has size n and is a collection of all trivial Quandle colorings. On the other hand, if the GCD of P and N is equal to C, not equal to 1, then the Quandle coloring space has size NC and consists of n trivial Quandle colorings as well as n times C minus 1 non-trivial Quandle colorings. So let's look at a sketch of the proof. Consider psi as a Quandle coloring. By the previous lemma, we know that p psi of x1 must be congruent to p psi of x2 mod n. In the case that the GCD of P and N is equal to 1, then the congruence can be reduced to psi of x1 congruent to psi of x2 mod n. And we can interpret this as psi mapping x1 and x2 to the same color. Now, if we consider the crossing relations of the torus link, x1 and x2 are colored the same under psi. This makes the third strand in their crossing also the same color. In turn, this forces psi to color every strand in our torus link the same. Since there are n choices for psi to map x1, we have that the coloring space has size n and is a collection of all trivial Quandle colorings. In the other case, if the GCD of P and N is equal to C, not equal to 1, then the congruence simplifies instead to psi of x1 congruent to psi of x2 mod n divided by C. This modulus is less than n, so we find other values in Zn that also satisfy this equivalence. We now have that psi of x1 is also congruent to psi of x2 plus nc, as well as other multiples of c. So this leads us to the conclusion for each fixed color in Zn, there are c possibilities for psi of x2 also in Zn that satisfy our congruence. Since there are n choices for psi of x1, we have that there are n C-Quandle colorings. Now we also know that n of these Quandle colorings are trivial. That means the remaining n times C minus 1 must be non-trivial. Moving on to results for Quandle coloring quivers having the same setup, if we let TP2 be a torus link and consider a dihedral Quandle Zn, if the GCD of P and N is equal to 1, then the full Quandle coloring quiver of our torus link is the complete directed graph on n vertices with a constant weight function of n. The proof of this comes from identifying the coloring space in this scenario as having size n. We also know that homomorphisms from the dihedral Quandle Zn to itself have the form phi sub alpha, where the alphas are determined by any two consecutive alpha. If we focus on the first two alphas, alpha 1 and alpha 2, we can fix alpha 1 and note that there are n homomorphisms of the form phi sub x, comma alpha 2. In this case, we have n maps leading from the Quandle coloring having all zeros. Repeating this but focusing on the alpha 2 and alpha 3 positions, we also have n maps of the form phi sub alpha n, comma x, comma alpha 2. In this case, we simply shift the subscript over. The other side of this theorem considers when P and N are not relatively prime. If the GCD of P and N is equal to C prime, then the full Quandle coloring quiver of our torus link is a join of two complete directed graphs by a constant weight function d, where d is equal to n divided by c, and the first component is associated with trivial Quandle colorings, and the second component is associated with non-trivial Quandle colorings. The proof of this theorem focuses on counting the number of Quandle homomorphisms from Zn to itself that send a particular Quandle coloring, psi with little x's, to another particular Quandle coloring, psi with little y's. In this case, we further focus on two subscripts in our Quandle colorings. Our map phi would need to send xi to yi and xj to yj. We need to recall that the subscript values of our map phi can be found recursively, and that the map itself is determined by any two consecutive subscript values. In this case, we can further focus on the value coming after yi that through the recursive formula yields yj in the correct position. By using repeated substitution, we eventually find a congruence modulo C prime that must be met in order for tau to yield yj in that correct position. And because C is prime, we have d possible values for tau in Zn that satisfy this congruence. Using the work listed here, we find the second component of our quiver as well as the nature of the joining. The first component of our quiver uses the same proof as the previous theorem. This leads to two corollaries. For a given P2 torus link in n prime, we have that if n does not divide P, then our full quiver is a complete graph on n vertices with a constant weight function of n. If n does divide P, then our full quiver is the join of two components. One, the complete graph on n vertices with a constant weight function of n. The other, a complete graph on n times n minus 1 vertices with a constant weight function of 1. In this case, our joining also shares a constant weight function of 1. The second corollary lets n be prime and considers two distinct torus links. If n does not divide P1 and n does not divide P2, then the Quandle coloring quivers of the two torus links are isomorphic. If n does divide P1 and P2, then both Quandle coloring quivers are still isomorphic. The proof of these corollaries can be found simply plugging in values into the previous theorems. So this marks the end of my talk. And again, I would like to thank Micah, Sujoy, and Rob for hosting this online seminar. Thanks for watching.